Good afternoon, everybody. Thanks for joining the webinar. My name is Simon Hart, and the topic is Battery Safety Regulation Load Cases using LS-DYNA Implicit. So the contents of the webinar will be the impact of electrification on vehicle design and analysis, safety regulations for battery systems used in electric vehicles, how we can use LS-DYNA to analyze these battery safety regulations, in particular using the implicit solver for durability and thermal cases. Then we'll look at new developments in LS-DYNA before finishing. So, as we all know, we're in a period of rapid change in the automotive industry. The carbon dioxide from road transport using fossil fuels makes up some 15% of global emissions, according to the Intergovernmental Panel on Climate Change in their 6th assessment report. Many regions of the world have now set targets for phasing out internal combustion engines and replacing them with electric powertrains. In Norway, this has effectively already happened, with nearly 100% of all new vehicles sold in 2025 being electric. In other countries, the target for phasing out internal combustion is 2035, followed by zero emissions across all sectors by 2050 to 2060, which is known as net zero. The impact of these changes on the automotive industry has been transformative. In a very short period of time, car makers have had to develop electric vehicles to comply with the phase-out targets and stay competitive in a very active market. We've seen many startups and new brands join the race to develop attractive electric vehicles. From an engineering viewpoint, all battery electric vehicles must accommodate what can be a very large and heavy battery, usually hundreds of kilograms in mass and taking up significant volume. This battery structure must be efficiently integrated into the vehicle structure so that it does not harm attributes like body stiffness and dynamics, durability and crashworthiness. In fact, if the engineering is done carefully, the structure can positively contribute to these attributes. Of course, efficient integration of the battery is enabled with simulation. Engineering the battery structure is an extra demand on the analysis team, who must provide feedback on the performance of the battery structure in many load cases, including for crash safety for legal and consumer requirements in different global regions. And actually, the battery is like an extra passenger in the vehicle that must be kept safe, just like the human occupants. And the battery also comes with its own requirements for safety. It comes with its own legal safety requirements that must be assessed before it can be sold with the vehicle. So let's take a look at these. In most regions of the world, there are safety regulations for battery systems used in vehicles. Generally speaking, they all have similar requirements for testing of the battery to ensure that it performs safely. There are mechanical tests such as shock, impact and crushing, vibration tests where the battery is shaken. There are thermal tests where the battery is exposed to large changes in temperatures, electrical tests to simulate overcharging or short circuits, and environmental tests such as water immersion. You can find regulations like these in Europe, China, North America, in fact most automotive markets, and a few examples are shown on the right of the slide. So let's look at the tests that are most likely to be analysed with finite elements. These are likely to be the mechanical tests and the thermal tests. You can see from the list of mechanical tests that there are some that are similar to crash cases that we would solve in LS-DYNA, such as impact and crushing. But some of the cases like vibration might be analysed by a different department in an organisation, for example the NVH or durability department, and they might use a different solver. And the same is true for the thermal analysis. This might be carried out by a different department, say the powertrain team, and they might use a different solver. And the downside here is that every time a different solver is used, it can introduce inefficiencies because we may have to develop a completely separate model or translate a model from one format to another. And all this takes time. We need to verify the model and check it's working okay, and that can lead to delays and feedback to the design process. In fact, many of these battery safety load cases can be analysed using LS-DYNA. LS-DYNA is a multi-physics code, and it's got a number of coupled solvers that are designed to work together. And in addition to the mechanical solver, there are thermal solver, frequency domain solvers, fluid solvers, and electromagnetic and battery solvers that will all work together. So if we have a battery model that's already been made for crash analysis, there's a good chance that we can use it for vibration and thermal analysis without many difficult changes. And this should give us a boost in efficiency because we only have to use one model in one format. Arup's a large engineering service company, and we're also the distributor of LS-DYNA in the UK under the Oasys brand. We write and distribute the Oasys LS-DYNA Environment, which is a suite of software tools designed to accelerate the workflow through LS-DYNA from model creation, solution, through to post-processing and reporting. And Arup also provides engineering services to automakers and battery makers to help them design their products to meet legal safety requirements like the ones we're looking at. And in every case, we recommend completing as much analysis as we can using LS-DYNA to maximize our efficiency and bring benefit to the client. So I'm just going to touch on the cases that can be analyzed using the explicit solver in LS-DYNA. In this case, a shock analysis on the left and crushing on the right of the slide. These cases are very similar to typical crash safety load cases, and in the case of crushing, quite non-linear in nature. Therefore, the explicit solver is a good choice. In these animations, you can see the example model being crushed and the force transmitted to the cells themselves, which is usually of interest. In the animation on the left, you can see an 8G shock analysis, which can also result in quite large displacements and material non-linearities, depending on the stiffness of the structure. So both these load cases can be short duration in nature and can be quickly solved using the techniques that most crash users would already be familiar with. When we consider the vibration and thermal load cases, the implicit solver in LS-DYNA is more suitable. The implicit solver capabilities include linear and nonlinear statics and dynamics, frequency domain calculations, random vibration and thermal analysis, and this makes it ideal for these battery load cases. What's more, the implicit solver is easily accessible in LS-DYNA, usually with the addition of a few extra control cards to the model and a few specific keywords. So let's start by looking at the vibration tests. In these tests, the battery is attached to a shaker table and shaken for a number of hours to simulate the lifetime of vibration that it might encounter on the road. The amplitude of the shaking is quite severe, around 1G, but not as high as the shock load case we just looked at. And depending on the regulation in question, the type of vibration applied could be harmonic or random. Harmonic means that the applied acceleration is sinusoidal in nature and of varying amplitude and frequency. For example, in ECE R100, the requirement is for a sweep to be applied, going from 7 to 50 Hz and back down to 7 Hz, with the amplitude varying between 1G and 0.2G over a period of 3 hours. This is done 12 times, each test being 15 minutes long. Random vibration means that the accelerations are random within specified limits. In the case of the Chinese regulation, the requirement is for alternating periods of random vibration followed by sinusoidal vibration. And this test is very long, nearly 40 hours, and the battery is shaken in all directions. Both tests require that the battery still functions after the test, so any failures within the battery that would prevent it from functioning are likely to be due to fatigue, since the testing will apply many thousands of cycles of loading to the structure. Therefore, we need a method in LS-DYNA to reproduce the vibration test and predict the fatigue life of the components inside the battery. We analyze the vibration load cases in the frequency domain. It's far more efficient and meaningful to use the frequency domain rather than the time domain because we can relate the response of the structure to its natural modes of vibration. These are calculated from a modal analysis. So we don't need to simulate hours of vibration in the time domain if we know how the battery will vibrate at different frequencies. In LS-DYNA, we can easily request a modal analysis simply by adding the star control implicit eigenvalue card to the model. Next, both harmonic and random vibration methods use modal superposition to calculate the response of the structure to the input accelerations. This means that the response of the structure is the sum of the mode shapes, each scaled by a different amount depending on the frequency. The two types of analysis we use here are frequency domain random vibration or frequency domain SSD, which means steady state dynamics. And that's the method we use for harmonic vibration. The modal superposition calculates the stress in each element at different frequencies. If we know how long the structure spends vibrating at different frequencies, we can calculate its fatigue life based on these stresses. The exact method differs depending on whether the loading is harmonic or random, which we'll cover in the following slides. So this slide shows the workflow for harmonic vibration. On the left are the inputs to the calculation. We've got the mode shapes and the frequencies that are calculated from the modal analysis. It's important to note that we also need the modal stresses from this analysis because we need those for the fatigue calculation. We also need the excitation to be applied to the battery in terms of an acceleration magnitude, frequency and direction. For UNR100, a sweep is required from 7 Hz to 50 Hz back down to 7 Hz, and the amplitude is a function of frequency, as you can see here in that load curve. We define this load curve on the frequency domain SSD fatigue keyword. On this keyword, we can also define modal damping for the analysis, which is usually a few % of critical damping for a lightly damped structure. We can also define where we apply the acceleration to the battery, which is usually at the mounting points. LS-DYNA will then calculate a stress frequency response function for every element in the model, which basically shows how the stress varies with frequency. The final step is to calculate the fatigue life. For this, we need to input a Voller curve or SN curve for every material we're interested in the battery. This curve defines how many cycles it will take to fail the material at different stress ranges. We then need to define an exposure curve, which defines how long the battery spends at each frequency. In R100, a logarithmic sweep is required, which means that more time is spent at lower frequencies to ensure an equal number of cycles at all frequencies. By combining the stress at each frequency with the SN curve and the exposure time, LS-DYNA can calculate the damage at each frequency. It can then use Miner's rule to calculate the total damage for the whole test, which is plotted on the model as a fringe plot. For random vibration, the workflow is similar, except for a few differences. For the loading, instead of providing a curve of acceleration versus frequency, we input a power spectral density, or PSD, as required by the regulation. A PSD defines how much power or energy is at each frequency, and it's a standard way to represent a quantity that's random. The modal superposition calculation is very similar to the harmonic loading method, except that for each element in the model, the result is a stress PSD instead of a frequency response function. We use the frequency domain random vibration fatigue keyword to define the input PSD, direction, locations of loading, and modal damping. We provide SN curves for each material as before, but this time the fatigue calculation is slightly more complex. By assuming the random vibration is Gaussian and follows a normal distribution, we can use the probability density function to calculate the probable time the battery spends at different stress levels based on the RMS value of stress in each element, RMS meaning root mean square. Again, LS-DYNA calculates the damage in each element to give a total damage value. With both methods, once we know the total damage, we have a good indication for each material whether it's likely to survive the test or not. But like all fatigue analysis, it's highly dependent on good data for the SN curves, and we have to take care with the model refinement, especially around details like welds. So I'm going to move on to looking at the thermal shock tests now and how we can model these in LS-DYNA. In the thermal shock tests, the battery is placed in a test chamber and the temperature is cycled between two extremes. For example, in ECER 100 from -40 centigrade to +60 centigrade. The cycle is repeated 5 times, with each extreme temperature held for 6 hours. The test is designed to test the battery's response to the rapid change in temperatures, which could cause damage due to the expansion and contraction of the pack and the change in material properties with temperature. The temperatures are achieved in the test chamber by forced convection normally, where hot or cold air is circulated around the battery in order to change the temperature. Because the battery's got significant mass, it may take a long time to reach equilibrium with the chamber temperature, which is why the soak time of 6 hours is needed. The test chambers work by forced convection with hot or cold air blown in to change the temperatures rapidly. This slide summarizes the main physical phenomena we want to capture in our LS-DYNA model. Firstly, the thermal loading onto the pack, which comes from the forced convection in the test chamber itself. We then need to model the heat transfer through the pack, which will be mostly due to conduction in the densely packed battery that has many metallic components in it. We need to model the transient response of the pack, since the test temperature is changing and the spatial distribution of temperature in the pack will vary with time. We want to predict the mechanical response of the materials in the pack in order to predict damage due to thermal expansion and contraction. And importantly, we may need to consider the effects of temperature on the material properties themselves, such as their Young's modulus or yield stress. Because of all these requirements, we need a coupled thermomechanical solution, which of course we can do in LS-DYNA. So this slide summarizes the workflow in LS-DYNA for the thermal analysis. To model the thermal loading onto the battery from the forced convection in the test chamber, we can use the boundary convection keyword, which requires us to provide a temperature time history and a coefficient of heat transfer. This controls the power available to heat up the outside of the battery. For heat transfer inside the pack, for a thermal analysis, each part must refer to a star mat thermal definition that defines its thermal properties, i.e. specific heat capacity and thermal conductivity. If we wish to, these can be isotropic or orthotropic properties. If parts are not meshed together but they are touching each other, we can model heat transfer via a contact surface with the thermal option. These contacts will model heat transfer between parts, and the power transmitted depends on the gap between the parts and other parameters set by the user. And although not shown here, there are control cards that govern the thermal analysis, and in our case we would choose a transient thermal analysis. To capture mechanical effects, we must run a mechanical solution that responds to the calculated temperatures. There are two ways of doing this that we have explored. The first is to run the thermal and mechanical solutions together in a simultaneous transient implicit run. This is the quickest method, and the structural solution can use a relatively large time step because we're using the implicit solver. The second method is to solve the thermal problem first and then pass the temperature time histories to the explicit solver. This can be done with the star load thermal bin-out keyword, where the temperatures from the thermal calculation are written to a binary file. The explicit structural run then applies the temperatures from the file during the structural run. You can scale the time values to suit the explicit time integration to avoid long run times. This approach might be useful if the mechanical model struggles to converge with the implicit solver. In order to predict the thermal strains in the structure, each material must have thermal expansion properties which can be added using the mat add thermal expansion card. Again, these properties can be isotropic or orthotropic if we want, and we can also define material properties that are temperature dependent. This might be important for polymeric materials whose properties can be sensitive to relatively small changes in temperature. There are several options for this available in LS-DYNA. The outcome of all this work should be a model that's capable of solving both the transient temperature distribution within the battery and the resulting thermal strains, and any potential damage within the battery that might affect its ability to operate properly. Arguably, the method could be extended to model the fire resistance load test, but because the thermal loading and temperatures are likely to be much higher, some further methods development might be necessary. So far, we've seen how we can use LS-DYNA as a single solver to address all of the mechanical and thermal tests required by the regulations. But how about the electrical abuse tests? There are several tests where the battery is deliberately overcharged or short-circuited or rapidly discharged to provoke some kind of failure. These types of failure can lead to a thermal runaway, which is another area of great interest to battery makers. The good news is that there are features in LS-DYNA that are available to model these phenomena. The Randall circuit capability in LS-DYNA allows us to model the electrochemical response of the individual cells in varying levels of detail. The ability to accurately model the charge and discharge cycles and the associated resistive heating allows us to study the consequence of abusive electrical loading. In Oasys Primer, there are dedicated tools to help the user set up Randall circuits definitions, including the different scales, for example, solid, batmac, T-shell or meshless. It also has an intuitive interface for Randall circuit parameter definition and tools to define arrays of cells, including options for busbar interconnection. Coupling the electromagnetic solver to the thermal solver allows us to predict the temperature changes resulting from current flow through the cells. As well as predicting the outcomes of electrical abuse, this ability also allows us to look at the cooling requirements for the battery. Most automotive batteries are liquid-cooled, and the design of the cooling circuit is critical for good performance of the battery. If we couple LS-DYNA's incompressible flow solver to the battery model, we can model how the coolant temperature changes as it's pumped through the battery and how well it flows around the circuit. The final piece in the puzzle is whether we can use LS-DYNA to simulate thermal runaway. It's not part of today's webinar, but this is an active area of development in LS-DYNA, and we can look forward to seeing developments there very soon. So, to conclude, the electrification of transport brings new challenges to the CA engineer and additional workload. Batteries themselves must pass unique safety requirements that have to be simulated. Completing as many of these regulatory simulations in one solver using a common model has obvious benefits for efficiency, and LS-DYNA provides the perfect environment for this with its multi-physics capabilities. The ongoing development by teams at Ansys and Oasys will ensure that we're able to simulate even more phenomena in the future. Thank you very much for your attention.